Now we come on to the next group of use cases, those from healthcare and life science. And this is obviously a very important subset because healthcare is such a um, important part of the economy, and saving money it is so important, and clouds are viewed as critical there. And also, there's been on the sort of research side enormous progress in areas like genomics. And though the feature of that progress is an enormous increase in the amount of computing that is used to process that data. So the first use case comes from a group at Indianapolis, and it discusses the sort of the core features of using electronic medical records. It comes from the Reagan Street Institute as who pioneered electronic records. And they point out that the EMRs are growing in importance as we build clinical support systems which have significant analytic capabilities behind them. And those are integrated with scientific discoveries to aid clinical treatments. And we are sharing health data as much as possible to improve both the efficiency and the outcomes. Because I say personalized medicine is best thought of, or at least one way of thinking about it, is doing the best possible comparison of a new patient to what happened to previous patients, and maybe using the equivalent of recommender systems to find the patients that best match the current patient. Um, so this requires health data, which are by definition is set up as electronic medical records, and we need to be able to link that data between different sources. So we need normalized ways of getting that information and recording the information. That's called having ontologies, which classify all the key things that we're trying to record. And we need to say to make certain that the information coming from between different sources is properly interpreted in a uniform fashion. Then we need to be able to select cohorts, namely um, like patients whose the evidence from which would be relevant. And the net result is clinical decision support. So this particular group has clinical data from a large number of health sources in Indiana, IMPC, which, as I mentioned, this group has pioneered electronic records. There's 12 million patients, 4 billion observations, 20 terabytes of data, and there are around a million new transactions per day. In the future, they expect to use not only SQL or traditional Teradata type approaches, Postgres, but also NoSQL, MongoDB, to be able to identify the relevant clinical features. And that's going to use the standard web search, TF-IDF, and document technologies, latent semantic analysis, which is related to uh, latent Dirichlet allocation to extract information. Natural language processing is important here, as it is in other applications involving documents, because so much information is captured in documents, and there's so many documents, we need to automate the processing. And then we're going to use large-scale maximum likelihood methods and Bayesian networks to build decisions. So this is sort of machine learning. Then these machine learning models will be able to work in areas such as diabetes, heart failure, and cancer. We will have a diabetes use case later on. So this particular use case 16 introduces a couple of important concepts in its classification. Electronic medical records is a very important item which we do parallelism over. It's interesting to note that the EMRs have one key feature, which is the patient. And being able to collect together all the information for a given patient is pretty important. And sometimes the parallelism will not actually be over individual electronic records, but rather over all of those records associated with a particular patient. We mentioned here the concept of fusion, and that's pointing out that in almost all these areas, we already mentioned this in the military application, you need to integrate diverse data to aid in either scientific discovery if the diverse data comes in science, decision making in our case here, where we have doctors sitting in the clinic looking at individual patients, going back to the back end, health data, running analytics to support their decision making. And this fusion varies all the way from very complex machine learning to do the integration through a portal, which just has different gadgets in it, one gadget for each source of information. Data fusion is one of the less well defined of the areas because its implementation and its actually input is so varied. There's so many different aspects of diversity, and it's different in different fields. The next use case comes from pathology, and it's another image base. So pathology is like an image, MRI image, or some image which is used to diagnose tumors and things like that, where basically you're taking a picture, and that picture is in 2D or 3D, and then you're looking for anomalies in that picture. And that's a classic image processing algorithm. And the feature of this problem, as we'll see, is that some of these images are going to and will continue to grow in size. And they're trying to find ways of taking images, classifying the features, using that classification to identify possible problems or non-problems with the entity from which the images came. So again, these images obviously are used for clinical diagnosis. I had an MRI to look at my back. That MRI was used by the doctor to diagnose what to do with my back. The next use case is pathology imaging. Pathology is an important area, and it's another one of these areas which has a huge amount of images. Remember, in the original, I pointed out that this year there's around 70 petabytes of medical images outside not including cardiology, taken each year. So that's a much larger source of data, say, than the Large Hadron Collider, and much bigger than most other sources. So these images are used to support doctors' analysis. An MRI image can help people diagnose what's wrong with backs, and other images have different will have different types of implications. This use case involves a MapReduce-like framework called Hadoop GIS, which is allowing one to build an image warehouse to support the analytics. These are called spatial analytics because images have spatial structure, and then that supports pathology. This particular work was actually done on FutureGrid originally and in prototype fashion. It involves, so you see here the Hive query engine on top of Hadoop, and it uses HDFS for the data storage. So it points out that you can do 3D pathology imaging by using basically either building things up from 2D slices, and then we can get larger numbers of three-dimensional objects from a single image. So this provides a much larger image space, a terabyte or so, with a terabyte of additional analytic results. And then a particular hospital might have around a petabyte of data. So this is a big data application. The actual results will involve probably machine learning on the particular images to be able to do the classification and things of the pathologies. And again, as these instruments gain in power and the analytics gain in power, we can expect significant progress here. So as I point out here, parallelism over images is a critical big data case, and that's important just because images are bigger than text. I mean, it's the number of when you have lots of pixels, there's actually the data is bigger, and there's sophisticated algorithms which take a lot of computing, and so text is a much smaller in size. So images are big. That's why they're important in big data. Notice we have parallelism over images and parallelism over pixels with images. So inter-image and intra-image are examples. The intra-image is actually being fully studied more than inter-image, but it may not be as important, even though it's technically very interesting and actually pretty hard. Another example of a sort of non-text thing, which will come later on in this group of use cases, is genomics, where we get sequences which also can produce huge amounts of data, which are very big and much larger than typical text data sets.